Hello everyone. So in this lecture, we're going to be talking about compounds. And compounds, just as an FYI, is when two or more elements come together, okay, to form either, in this case, ionic compounds, which we're going to be talking about in this video, covalent compounds, and metallic compounds. Okay, so this is a very important periodic table here. So it shows you the metals and nonmetals. And the three types of compounds, metallic, covalent, and ionic compounds, are based upon what type of elements actually join together. So in this case, if you have a metal and a nonmetal, that will be an ionic compound. If you have two nonmetals, and remember again, hydrogen is a nonmetal, you actually get a covalent compound. And then if you have two or more metals, that would be a metallic compound. Please just note that there is one exception in which no metal is present, but it's still considered an ionic compound, and that's the presence of this thing called ammonium ion. Okay, so that is also, anytime you see that, as well as any of these metals, that will be an ionic compound. So why do ionic compounds occur? Well, what we're going to do is we're going to look at this electron configuration of the noble gases, helium to radon, and it's shown here. And if you look at the electron configuration, the most important thing that you should pay attention to, folks, is the valence electrons. And again, the valence electrons is by looking at the highest energy level and looking at how many electrons are on the highest energy level. If you look at this, you should see that except for helium, all the noble gases have 8 electrons on their outermost level. And 8 or 2 for helium for for period 1 elements are the most stable electron configuration, because all of the orbitals are filled in this case. So what happens when a metal and nonmetal join together? So let's look at sodium here very quickly. So sodium, folks, is 1s2, 2s2, 2p6, 3s1. And then if it's joined with chlorine, chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So again, the most stable configuration is when you have 8 electrons on your valence shell or your outermost shell. So sodium can hypothetically, theoretically get 8 on its outermost shell by 2 ways. It can either gain 7 electrons to make this 8, or lose this actual electron. So notice that if I eliminate 3s1, you now have 8 electrons on your outermost level. Octet rule. Similarly speaking, if you look at chlorine, chlorine can also do the same. It can actually lose 7 electrons or gain 1 more to make it 8. Right? So FY, if chlorine gains 1 more to make it 8, it will actually look like argon in this case. So that actually makes it highly stable in terms of electron configuration. And this is what happens when you have, in this case, a metal and a nonmetal, because sodium would want to lose this electron, but chlorine wants to gain this electron. All right? So that is why in an ionic compound, the metal normally is positively charged. In this case, sodium is positive 1 charge because it has lost 1 electron. And the nonmetal becomes negatively charged. In this case, chlorine, since it gained 1 electron, becomes a negative 1 charge. Okay, so in this case, you actually have the ionic compound sodium chloride. And again, the reason why that is because both of them wish to have an electron configuration similar to the noble gases. So similar to what we've talked about previously about sodium losing electrons and chlorine gaining electrons, there's actually a trend that you can actually see by looking at this table here. Group 1 will normally lose 1 electron, so it has a +1 charge, so on and so forth. However, the flip side is group 15, 16, and 17. Group 15 would like to gain 3 electrons. That's why nitrogen and phosphorus is -3 in ionic compounds again. All right. The only exception, folks, is hydrogen. Hydrogen does not have a +1 charge unless it is in an acidic solution. Okay. There's also something special called polyatomic ions. So these are monatomic ions. It's one atom with a charge. In this case, as you can see, this has 2 atoms with a charge. That's why it's called poly, meaning many, atomic ions. Okay, memorize this. This is in your exam reference sheet. And one of the most important thing is you need to know how they look like, plus their charges. Something weird happens. I don't know if you guys can see this, but there is something, as you can see, the charges for the D block elements and even the F block elements are not shown. And the reason why, if you look at this area here, is the D block elements, except for scandium and zinc and silver, actually can have more than 1 charge. Like titanium can actually lose 3 or 4 electrons. Vanadium can lose from 2 to 5 electrons, and they are called variable charge metals in ionic compounds. And this is gonna have something to play when we're gonna start naming or writing ionic compounds soon. So back to my piss-poor drawing. If you put joint sodium and oxygen atoms together, again metal and non-metal, they form this compound called sodium oxide as an ionic compound. Why is it Na2O? Well, sodium, as we know, is in group 1, so it loses 1 electron, so it becomes +1 charge. And oxygen is group, in this case, 16, so it gains 2 electrons, so therefore it gets a charge of -2. All right, so loses 1, gains 2. The problem is the number of electrons lost and gained in any compound must always be equal. So right now, someone is only losing 1 and someone's gaining 2. Right? This is not Hogwarts Castle where things happen by magic. So the way that you balance that you get oxygen 2 electrons is by having 2 sodiums, as indicated in this molecular formula. Okay, so in this case, sodium, there's 2 sodiums and 1 oxygen atom in sodium oxide. Okay, there's a shortcut in trying to figure out, in this case, subscripts. These are called subscripts. The charges are normally written as superscripts, and it's called the crisscross rule. In the case when you have magnesium and nitrogen atoms joined together, as you can see, the charge of magnesium is 2+, and the charge of nitrogen is 3-. All you do is you crisscross. So this 2 goes underneath nitrogen, that 3 goes under magnesium. And if you do some math, you can see that 3 times 2 is +6, and 3 times -2 is -6. So the numbers of electrons lost and gained in that case is actually equal to each other. What happens when you have polyatomic ions? So here you have ammonia with a +1 charge, and you have a phosphate with a -3 charge. Well, what happens is this 3 goes here and this 1 goes there, and we never write 1 down. Do not write the 3 down without enclosing the polyatomic ion in parentheses. Anytime there's more than 1 polyatomic ion, the polyatomic ion has to be in parentheses in this case. Okay? So again, very important crisscross rule. And again, that's to make sure that the numbers of electron loss and gain is equal. So what happens when we go from a formula to a name? So in this case, we have magnesium and oxygen. It's a binary compound, meaning there's only 2 elements involved. So in this case, it's just a straightforward write the name of the positive ion, magnesium, and the name of the second atom ending in IDE, magnesium oxide. And FYI, this is no different between covalent compounds or ionic compounds. Binary compounds will always have IDE ending, except for hydroxide, which is a polyatomic ion. Here we have sodium chlorate, and the reason why this is called sodium chlorate is because it's a combination of the metal sodium and the polyatomic ion chlorate. So in terms of polyatomic ion, you just need to copy the name of the ion down and write it the way it is, sodium chlorate. Note that ATE or any other endings except for IDE indicates that there's more than 2 atoms present in a compound. Here we go. This is much more confusing. So copper chloride. Now recall that copper is one of those elements that can have more than one charge. Okay? So in this case, we need to identify what is the charge of copper in this compound when we write this down. The compound name is copper 1 chloride, and why is that? If you look at it, copper in this case is joined with chlorine. We know that chlorine gains 1 electron. There are no subscripts, meaning to say there is 1 copper and 1 chlorine. So therefore, if this one is gaining 1 electron, copper must be losing 1 electron. So this is where that Roman numeral comes from. And this is the same for all of the D block metals except for silver, cadmium, and zinc. You always need to write the designated charge in Roman numerals. Okay?